And get started. I guess we'll do a week in advance real quick just so everyone's on the same page. Today's Monday, we got Tuesday, Wednesday, and Thursday. Wednesday we're having a test over chapters 8 and 9. And as always, you know, if you want to start early, that way you can go from 7:30 to 9:30 and get a solid 2 hours in on the test if you want. On Tuesday, we're going to finish the titration lab. And on Thursday, we're going to actually lecture on chapter 10, starting basically, well, it's some quantum mechanics, but it's basically the structure of the atom. And what it allows us to do is get enough information about electrons to go on to chapter 11 where we talk about how molecular compounds are made. We kept putting it off and off and off, and so finally we can get there. And so today what we'll do maybe is a little review to start, or maybe we'll answer some questions. Because really we said one of these 2 days you kind of have to turn in chapter 9E homework. Otherwise, you know, it doesn't do you much good to turn it in Tuesday night and have the test Wednesday morning. So what type of questions do people have? Otherwise, what I'll do is I'll do at least a semi-brief just overview of everything and what you guys should, you know, maybe think about how you're organizing it or where you're at.
Do you have any in front of you?
Sure, if I dig around. Why, there it is. What do you know? Okay, so question 6. I don't have the details, I have the answer. So let's do one like question 6. Question 6, like. Now we did one of these in our notes. Did you make sure you went and kind of checked that out?
Yeah, sometimes I don't know, it just doesn't make sense to me when I read it.
Okay.
How I got there, you know what I mean, why I decided to put those things there.
Okay, so let's just take a look at how we can approach this problem. So we're given a reaction. We'll make up our own reaction. We'll react H2SO4 plus NaOH. And really, we don't care about the other part of the reaction, right? Meaning we don't care what it makes. All we need to know is the mole-to-mole ratio for the reactant. So we'll just kind of leave it at that. And then let's see. This says that you've got well, let's do it this way. How about 10.5 grams of H2SO4? And then the question says, how many milliliters of 0.1, we'll make it different, 0.250 molar NaOH is required to react completely with H2SO4. So what we said is, and maybe I'll go on to a new slide just to put some of these details down, but I see people are still writing the question down. Remember, kind of think about it in terms of the tools that you have. Meaning, the tools that you know from this chapter are the definition of molarity is moles per liter. We know molecular weight is grams per milliliter. And we know that we can have a mole-to-mole ratio if we want to go from talking about, and maybe I'll even make it explicit, moles of A to moles of B. And so those are the only 3 conversion factors that you have to use on these problems. Now, obviously, you know, you still have your cheat sheet, so we can throw in a few metric ones, because we know we're always converting between milliliters and liters every time we use molarity. And then the approach we want to take to this is, you know, organize your information. Meaning kind of put it in, you know, what info do I have and what answer do I need? Good morning, Jess.
Good morning.
How are you?
I'm doing pretty good.
Not quite good enough, though. Nope. So the second part is realize you never start with the conversion factors. meaning you never start with molarity, you never start with molecular weight, you never start with a mole-to-mole ratio. Now, you might start with a metric conversion if you're given information in milliliters and want to convert it to liters right away. So you never start with a conversion factor. And then remember your general chart, which is moles of A and moles of B are kind of in the middle. And so notice that, for instance, if I want to know something about H2SO4 and I'm given information about sodium hydroxide or vice versa, at some point I have to have a mole-to-mole ratio. So if nothing else, work towards that point, that this is in every single problem, right? Almost every single problem uses this. Now, that being said, the ones on the front page of the worksheet don't use the mole-to-mole ratio too much because those are just setting up definitions of molarity, right? So when I say almost every, I mean the really tough ones will use this, and the rest of them probably not. And then also realize that you've got various paths, meaning you know how to get from grams of A, and you know how to get from milliliters of A, and you know how to go to grams of B, and you know how to go to milliliters of B. That this is our molarity, this is molecular weight, molarity, and that this is that mole-to-mole. Meaning that chart right there, if you follow it from one side to the other for like half the problems, that's exactly what you're doing. And so if you can recognize that you always want to work towards that mole ratio of A and B, then you can do it. Now what we'll look at after we do this problem is how to decide, am I doing a problem that involves this chart, or am I doing something kind of simpler, like the first few questions on that worksheet were simply, calculate the molarity of this. And you didn't need a mole-to-mole ratio for that, right? And so there's kind of one way that we can tell if we're going to use a mole-to-mole ratio in a question or not, and I'll talk about that after this question. How about, just remind me, okay? So those are the tools you have. This is the approach you want to take. So for this specific problem, if we take a look at our info, we know that we have 10.5 grams of H2SO4, and we know that we had what, 0.250 molar NaOH. And we know that at some point I will have to get to milliliters of NaOH. So to me, and I have to admit, I do this all the time, so maybe it's not as obvious to you. And what you need to do is learn how to make it as obvious to you, meaning pick up on these patterns, pick up on these trends, pick up on the way we think about these questions. You've got only two places you can start the question, right? You can either start with the grams of H2SO4, or you can start with the molarity of NaOH. Yeah, almost never. I won't say you can't do it, meaning certainly with bar problems, as long as the units cancel, it doesn't matter where you start in the problem. You can start backwards if you want, or you can start right in the middle. I mean, technically, you could start with a mole-to-mole ratio if you want. It's just logically, it doesn't make any sense to a certain extent. And so we know that we're going to start with that 10.5 grams of H2SO4. Now, once you've got your starting point, then you have to decide what to do, right? So we've kind of worked on how to pick your starting point, which is don't use molarity, don't use molecular weight, and usually there's probably only one value after that. Now some types of problems have two values. You're going to have to use a little bit more thought, but in this case there's almost no choice, right? And then rule number two is kind of, and I didn't number the rules, so I just make the numbers up. Another rule, how about, is what do we know we're going to have to do? I mean, if we're talking about H2SO4 and we're talking about sodium hydroxide, at some point you need that mole-to-mole ratio, right? Because you're talking about two different things. So the idea is just work towards that mole-to-mole ratio. And really, I got to be honest, you only know how to convert grams into two things. You can, well, okay, three, but we said we're not using density this chapter. So we're not going to use density either. So you can only convert grams into atoms and moles, and even to get to atoms you have to go to moles. So really, if you take a look at your tools, I mean, you only got one tool that has grams even in it. So to me, that's the next logical choice. H2SO4 is in 1 mole of H2SO4. And of course, does anyone that's working on this on the side figured out a molecular weight yet for it? 98.08 if I round. Yeah, I was going to say, I remembered 98 sticking in my head, so. But sometimes other things stick in my head, like the stupid song I heard going home last night that kept me awake all night singing it. Oh. I've listened to music since then, so it's not as much in my head. No, the worst one was when my brother's kids serenaded me with "The Wheels on the Bus Go Round and Round."
Oh no, that's way worse.
And they know like 50 verses to it too, and they serenaded me for like half of it. I think my brother was pissed off at me.
So that's what was stuck in your head all night?
No, that was another time. I'll have to think about it when I'm not thinking chemistry. See, right now I got so much chemistry in my head. Okay, so here's my molecular weight. And again, now that I'm in moles of H2SO4, arguably I've only know a couple things I can convert moles to, right? I can convert moles to liters if I know molarity, but I don't know that for this. I can convert moles back to grams, but that's going backwards. And so normally in the middle of our problem is that mole-to-mole ratio, so we're going to go moles of H2SO4 to moles of NaOH. And so we know that it's a 1-to-2 ratio from the balanced reaction. And here's where, the problem changes a little bit. So now notice that I was talking about H2SO4, but now I'm talking about sodium hydroxide. And I got to be honest, worst case scenario, you know that at the bottom of this, you have to have moles of NaOH to cancel out, right? And again, I can convert moles to grams of NaOH, but does that get me any closer to milliliters? Not really. So here, I want to go from moles to liters, and I've given that one 0.250. So that's my molarity conversion factor. And also remember, maybe that's something I should put off to the side, but we talk about molarity, but we never use it in a problem. Right. Well, it's not because it's a conversion factor, but because molarity really stands for moles per liter, meaning there's two parts to it. And so use this. Never type capital M in a problem. Type capital M in the answer if you want. In fact, if you want, never type capital M at all. Just always put your answer in the answer blank as moles per liter. That's the same thing as capital M, right? And so because it's got two sets of units, you'd never want to use capital M in a problem because then it would be hard to keep track of which unit's being canceled. So never use M. Bad. And so our last step is, of course, just 0.001 liters is 1 milliliter. And since we made this up, we'll type it into our calculator. 5 times 2 times, oops, nothing else, divided by 98.08, divided by 0.250. And I think if I remember right, I only had 3 sig figs and everything, so 17.98, so that's really 18.0 milliliters of, well, maybe I typed it in wrong. 10.5 times 2 divided by 98.08 divided by 0.250. Oh, now I got something different the second time I typed it in. Did you get 0.856? Yeah. Okay. See, this is always a good thing. I got to be honest, on a test.
I got 850.
Oh, I forgot the 0.001 divided by 0.001. There we go. Okay, Jay's needs to wake up this morning. 856 milliliters of NaOH. So notice that I've got a number, I've got a unit, and I've got a compound. So make sure you have all those in your answer. So, limiting reactant. You're given two things, so you need a limiting reactant. But let's talk an overview. Types of problems. One of the things I always tell students, or people in general, is that if you don't have an overview, if you don't know what might be out there and how to think about how you're going to figure out each type of problem, then you don't know where to start necessarily in a problem, right? And it's not always obvious, and I can't give you a hard and fast clue how every problem will be worded. But some general rules, if you're only given one reactant, then basically it's just a conversion problem.
For chapter 9.
Right. Meaning, you know, I might say, you know, an example of that would be, you know, how many grams of HCl react with, you know, 10 grams of NaOH. Or, you know, I want to make 50.0 grams of H2O. How many grams of CO2 do I need? You know, basically there's one thing that's being converted to another. Meaning it's simply going to be your standard problem where you go from grams of A to moles of A to moles of B to grams of B. Now, that can change because remember, it could also be milliliters to milliliters. So, you know, we can word the problem in a number of different ways, but in this case, it's you're only getting information about one compound, right?
Yeah.
And, you know, if you're given information about two reactants, then almost always that means that the very first step you have to do is calculate the limiting reactant. And that then includes all sorts of problems like, you know, if you ask for how much of the excess reactant is left over, well, to figure out the excess reactant, you still have to calculate the limiting reactant, right? And if you're asked for theoretical yield, you know, you still have to calculate the limiting reactant, right? Meaning, limiting reactant is the very first step for most of those problems. And what did we have? Oh, limiting reactant, excess reactant, theoretical yield, how much of the product is made, or how much of all products and reactants are made. And heck, we even threw in some conversions to kilojoules, right? Meaning how much energy is required for the reaction to occur, or how much energy is released. Now, contrast that if you're given two reactants and the word neutralize. That means that it's a titration problem. And that really is, again, just a conversion, like way up here. And to be honest, the difference is for the given two reactant questions, you have to be given, maybe I'll put this in red. See, this has all the information. And maybe I'll expand on that. All the information means that I know either grams of A and grams of B, or if I know milliliters of A, I also have to know molarity of A, right? And if I know milliliters of B, I have to know molarity of B, meaning that there's all the info. Whereas for like a titration problem, you're given something like milliliters of A, milliliters of B, molarity of B, and you might not know the molarity of A, meaning one of those four pieces is missing. And so my definition of all, meaning I know what all means, but sometimes it's not obvious to you guys. So all means that you really either know both grams, or you know both the number of milliliters and the molarity, since you can't calculate molarities, you know, from a periodic table. And so that really probably sums up the majority of the problems in here. I would say the only other kind of miscellaneous category, and I don't tend to put too many, well, like I'll put one miscellaneous one on there, is just what I call definitions. Meaning questions like, what is the molarity of the solution?
So like the first page.
Yeah, like first page of 9E, meaning you can ask a few questions, you know, but here you notice you're given both the moles or grams and the volume. And I don't know. I try, seriously, I try to think about how I recognize all these questions and what I'm doing. And part of it is I just have done it so much that it's like almost instantaneous. Although, frankly, if someone else were to give me a test that they wrote, maybe their wording would be different and I'd have to stop and think. So what I'm trying to do is break down some things that go through my mind when I'm thinking about a problem. Meaning, if I see two reactants, I'm either thinking, you know, maybe a limiting reactant question. Or if I see the word neutralize, I know that it's one of those two last questions on homework 9E, for instance. And so there's a variety of different ways to approach these. But I got to be honest, you can always, worst case scenario, fall back on, you know, all the definitions, right? So you should be able to kind of do those conversions. But it also helps to have that big picture, I think. Does the big picture make sense? I mean, I have to admit, you know, all of these are kind of, they're without examples. And so the other way to really get good at this is you just have to practice it. Meaning, go and, you know, do the practice on the internet. Make sure when you read through the homework you say, okay, if I had all my homeworks just shuffled together and mixed up, would I know what I'm doing for each type of question? Quiz each other. Go and take one question per homework, and don't even use the exact same homework question. Just make up a random reaction in a random amount of grams or moles or something and say, okay, how would we solve this? And if you guys make up a question and you're not sure if you have the right answer, come see me and I'll do the problem myself. Or, you know, if you guys both work something out and come up with something different, or, you know, have an argument over it, you can either arm wrestle or you can come ask me.
We'll arm wrestle over who has to do it.
That would be fair too. I don't think I've bit
What about
anyone's.
chapter 8?
Okay, so that's chapter 9 in a nutshell, meaning the approaches to take. I really think that if you can solidify in your mind what tools you have and use them, and then, you know, kind of figure out that starting point, you'll be okay.
Yeah,
For-
don't do that. Don't do that.
For chapter 8, what I really think the very first starting, well, gosh, I don't know. I would say the first thing you have to do is recognize the reactions. And that's that handout I gave in class that I'd never have a copy of, apparently, because I gave it to someone. So, no, I'm just going to put it up here on the web real quick. Slow. Recognize the reactions. Why is my mouse... Holy slowness, computer. So we need to tell Todd that if we're doing lecture capture, we need to have better computers. So what I'm talking about is this reaction table is what I called it. And so notice that the very first thing on that table, kind of in the upper corner, is what I called one-year triggers over here. I guess you can kind of see where my arrow is pointing, where it says triggers. Meaning, how am I going to tell whether I'm doing a combination, decomposition, double displacement, acid-base, single displacement, or a combustion reaction? If you can't figure out what reaction you're doing, you're going to have an awful hard time finishing it, right? So that's the key. And we went through this in class, I thought, real quick after class one day. But has everyone kind of figured out how to tell which type of reaction you have? Did you practice those 3 extra practices that I gave out that have all those mixed together? Yeah, Jay. I'm sorry, what?
The 2 worksheets that you helped me out on?
Yeah.
I don't think I have them back yet, but you put the little, like, the type of reaction.
Yeah, I graded everything and handed it back. You sure it wasn't sitting on the desk right in front of you? Because I handed you back 2 worksheets today. Now that's chapter 9. You're thinking chapter 8. I gave that back quite a while ago. So that was one question. I didn't actually print out those extra 3 sheets because some people will do them and some people won't, and I'm not going to waste paper. So if you want them, you can print them out. And it also includes the answer keys with it, right? So, and remember, the 3rd one is new this year. Who knows if it's got a typo here or there.
Well, I'm hoping that it does.
Has you got some
Yeah,
questions?
for credit.
Oh. Yes, that is also true. Extra credit for all typos and mistakes Jay makes. So the key here is the triggers. So notice that mostly the triggers depend on whether you're talking about compounds, elements, acids or bases, focusing on if you see oxygen in the reaction, And then I got to be honest, the two tough ones are the combination and decomposition. So I'm going to tell you this right now. For the combination reaction, I never put the beginning point. You'll never get two reactions, or I'll tell you it's a combination. Meaning there's no way to tell the difference between a combination and like a double displacement or single displacement. And so there's no combinations on the test. Or at least if I put combinations on the test, they're always like this. Yeah, or I'll put it in a section that's labeled combination and decomposition reactions only. So the combination ones, there might be one on the test, maybe two. I don't know. It depends on what sort of mood I'm in. And so really you only need to know the last 5 on that chart, right? So does everyone think they can recognize the type of reaction? Have you memorized that? Okay. Let's see. Notice that I'm trying to keep them almost the same, right? Oops, that's not a solid. So there's 4 reactions that we can practice on. So the first thing I do is simply go and tell me what each of those 4 reactions are. So I'll give you a second to write them down. And notice that I made the first 3 as like as I possibly could, meaning they all have sodium hydroxide in them, right? And so the key here is to do that. And then maybe the other thing to remember off to the side is you also have to have an idea of what steps you want to do in a reaction, right? And each reaction is a tiny bit different. Some of them you have to check and see if they occur. Some of them you just know they occur. Some of them you don't even need to bother to check if they occur because you know they always happen. So there's all sorts of little specialties for each type of reaction. So, but I got to be honest, the first key is to recognize it. So what's the first one? Okay, what's the second one? And well, remember the decomps, well, they're pretty straightforward as far as for a decomp, remember it's one reactant breaks apart into 2 products. So you might have something like this, meaning the nice part about it is it's the only one with 1 reactant. So if you only have one thing over there, you know exactly what it has to be. No, this is just an example. Arguably, if it has a dot in it, it's only going to be a decomposition, but there are other decompositions that don't have dots in them. Another example would be oops, that doesn't need, well, here, we'll do it this way. I don't know if that's aqueous or not, but we'll say it. Meaning it can just be one thing though, right? Okay, so going back then, what's the trick to remembering single displacements? Maybe we'll put it, what? Yeah, you have to look at the activity series, right? And you also have to decide what to swap. So in this case, should I swap and write, do I do like NaMg plus OH, or do I do MgOH plus Na? Yeah, what's wrong with this? Yeah, so remember when you're swapping stuff around, in those back of your head should be weird things like, if I see 2 metals together, that should look funny. You know, it's not like we're just playing alphabet soup where you can stick any of the letters together, right? They actually there's some rules. And one of the basic rules is cations don't like cations, anions don't like cations.
But that would be a no reaction because sodium has a higher activity.
Well, yeah, that's the other thing we have to check. Remember, we said activity series. So here, sodium is more reactive than magnesium. Therefore, sodium is in the compound.
So question on that.
So really, that's a no reaction one.
Do we need to write all that out before we figure, can we just put no reaction if we know it's a no reaction?
If you just know it's a no reaction, go ahead and put no reaction.
Okay.
Although
You
on the
don't need to,
test, I
like,
might
make
add.
crazy-
No, you don't have to do any of that other stuff. This is just, we're you know, not necessarily doing everything in the exact order we do. Like, for instance, I really think it's helpful to figure out what you're swapping, because I've seen people do things like this, you know, where it's no reaction because they were comparing sodium and chlorine.
Right,
You
yeah.
know, so, meaning I like to at least write this step out so you know kind of what you're comparing, the sodium and magnesium. Either that or I'll just put arrows just so that I can see it visually. So the arrows help me to decide that I'm comparing the right things.
So, but we don't have to do that. You're not gonna Microsoft, you're not gonna.
No, if you just put no reaction, that's fine.
Okay.
Now, I might throw a curveball at you on the test and ask you why it's no reaction. If there's no reaction, state why.
No, that's easy enough.
I know, hopefully. Okay, what about double displacements? What do we have to remember? Swap cations, and then we have to check solubility, right? And again, could you check the solubility without swapping the cations? Yeah, you could do that step in your head. You really could. And if it's a no reaction, you could do that in your head. Wonderful. I'm not that good, so I swap the cations, and then I look up the solubilities, right? Yeah, and see, this also should trigger something, right? Because I asked you to memorize 3 decomps. Honestly, seriously, if you can't remember 3 things, just go work at McDonald's. Because usually McDonald's, well, heck, even McDonald's orders are 3 things.
You gotta remember a lot, actually.
I know. Waitressing is not easy. McDonald's, you have to remember to look at all the damn pictures on the register.
Or how to put together a burger.
What goes on a burger? You know, maybe McDonald's and chemistry are a lot alike. I mean, you don't forget the pickles on your McDonald's burger.
You know, you have to
And
memorize the whole menu.
the weight, like how many grams it is.
Yeah, because like every meal has a certain weight, so it's like even for each time it's ordered, it has to be a certain weight.
Yeah, you're recording during the
Yeah.
Actually, a lot more involved than you think.
Silly.
Yeah.
Anyway, so we should remember that that really breaks down into NH3 gas plus H2O liquid. Notice I've also gone on and done a bunch of other steps, right? We should always put states in, meaning you're always doing states, your diatomics, your charges, and you always have to balance the reaction. And notice that's stuff that I haven't listed down. That's on another part of that sheet, but that's another thing that you have to have in the back of your mind. And I highly recommend on the test that once you're done with the test, do what I call, well, basically go through it a second time and make sure you didn't make any idiot mistakes, or sometimes I call them brain farts or anything like that, where like literally the only thing you do is on all the reactions just make sure you put a state. Because it's so, like I'm grading homeworks or a lab, and every once in a while there'll just be a problem where you don't put states down. That's 2 stupid points to lose on a test. Because if you put them down for every other reaction, you know, you probably would have put them down for that reaction, right? You know, same thing with going through every calculation in chapter 9. Simply say, I'm not going to worry about the actual calculation. Who cares? I'm going to look at the question, I'm going to look at the answer and check sig figs. Just to make sure I didn't forget in the problem or stop halfway through the problem and just forgot about it totally. Or, you know, go through and say, I'm not going to worry about whether I did the reaction right or not, but I'm going to double check all the charges on everything. Or, you know, do everything separately instead of in a string just to make sure you didn't, you know, screw up something. So then we have to balance the reaction, and I picked a nice easy one. It's all 1s. You don't have to put the ones in there, but I'm just going to put them in there to show that we did it. And because I can have different colors, I'm just going to do that. So some people told me that it's an acid-base one. And what we should remember about acid bases is it's really just a double displacement plus heat, right? So when we do the double displacement, we take and we swap some stuff. Whether you write it out as HOH or H2O, I don't care. Just don't forget the heat. That's another just, idiot point. And you can just tell yourself, okay, at the end of the test, I'm going to double check all my acid-base reactions. And, make sure I added plus heat. What other reaction gets plus heat? Combustion. And I mean, part of that is like I should be getting a chorus every time I ask a question. All 10 of you, well 9 since Oksana isn't here, should be saying combustion, not just Jay and someone else. I don't know, I wasn't paying attention over here. I only recognize Jay's lovely voice. He should like narrate books. I'm just kidding. I have no idea. I don't pay that much attention. So the nice thing is we know these reactions always occur. I guess we technically don't need a line for plus heat. We do have to remember to balance the charges, so we can go and put those in and realize that we need 2 sodiums. And then we can go and balance the reaction. We realize we need to put a 2 in front of NaOH and a 2 in front of water. And then we know we have to put the states in. So, these steps always apply.
You said acids are aqueous, right?
Yes. So like sulfuric acid and sodium hydroxide would be aqueous if you looked them up in the chart. And then the last one is combustion. That again, really you just have to memorize it. In that we know it always goes to CO2 plus H2O plus heat. And so the hard part about this is simply balancing it. So, we got 1 carbon, I've got 2 of this. That means I've got 4 oxygens on one side, but I've only got 3 on the other. So I can't make it work. So then I know I have to double this and double this and do this. Let's see, 8, 8. So now I've got 4 and, wait. 4 and 4 is 8. Jeez, Jay. Minus 2, so I need a 3 there. So really the hard part of the combustion reactions, I think, is remembering to balance them. I think like single displacements are pretty easy to balance. Double displacements are always fairly easy to balance once you get the trick of the charges. The combustion ones are the ones that are a little tricky.
So in that combustion, you have H2O, you have the state as a gas.
Yes, we said that for combustion reactions, there's almost always enough heat generated that the water really is, a gas.
Okay.
Because, go ahead.
No, you can finish.
That's what I was always going to say.
So the acid base and combustions, they always occur, and then double displacements, you see if like you're both aqueous on the product side, then it's no reaction.
Right.
And then the other ones is in the acid.
Right. This has to produce either a gas or a solid.
You have to put no reaction if you found out that it.
Yes, you put no reaction in the answer blank. Otherwise, I can't tell if some of it's your scratch work or something else.
The other
So
way
that's
you
why I
can
added the no reaction there.
put nothing.
Nothing else in the other answer blanks. And the reason I do that is because sometimes it is nice to show your work, right? And I mean, at the beginning, when I first started teaching, people would just like put something down in the answer blank and go, well, obviously there's no reaction, I didn't finish it. And it's like, no, that's not obvious. You could have just not finished it because you're an idiot. I didn't say that out loud back then. Now I do. I think loudly sometimes.
Okay, anything else you feel like we need to know?
For
Throw any
reactions?
crazy shit in there?
Well, I mean, we did talk about and have in there exothermic
Good thing I'm not.
and endothermic. So this means you have to remember chapter 4 plus what we learned about it in chapter 8. Or was it chapter 9 that it got stuck in? 8. Which basically means that we can really 2 new things. The first is the charts had a new feature added to them. So if this is my reactants, this is my products. Now the types of questions I can ask are label everything, you know, draw the actual graph, and you know, I can say label the activation energy. I can say label the amount of energy released, or absorbed, I guess, in this case. I can ask you whether I just drew an endothermic reaction or an exothermic reaction. You know, I can ask a multiple choice question which simply says something weird like activation energy. I can ask you what the activation energy is. I can ask you weird questions like, you know, in an exothermic reaction, is the energy of the products higher or lower, which really, or I can phrase it as a true false, you know, in an endothermic reaction, the energy of the reactants is greater than the energy of the products. I can, you know, I can even do things like this, you know. Exothermic, reactants, products, you know, put a sign, you know, or this, you know. Or I can, you know, there's all sorts of ways I can phrase it. Is the amount of energy released less than or greater than the activation energy? The best way to figure this all out is to kind of know the basic facts about endothermic and exothermic reactions. Or for instance, when in doubt, draw the picture. It might visually give you the answer to a question. Like for instance, you know, this first question right here. In an exothermic reaction, the energy of the products is higher or lower than the energy of the reactants. I got to be honest, without drawing the picture, I have a hard time telling that. You know, I'd probably draw the picture. No, you can draw it on a piece of scratch paper on the back of the page if you want, or wherever you want. You know, if you want to draw the picture. Or, you know, we know that, for instance, you know, we can have this. Energy, is this an endothermic or exothermic reaction? Yeah, it's an example of an endo, meaning the energy is a reactant. So, meaning there's so many ways I can phrase those questions. I don't know if you think you can study for them all, other than to really know what endothermic and exothermic kind of mean. Oh, we can work them out. For instance, in an exothermic reaction, is the energy of the products higher or lower than the energy of the reactants? It should be lower, right? Because excess energy is released. In an endothermic reaction, the energy of the reactants is greater than the energy of the products. This is false, right? I mean, heck, you can just look at this picture, and if you can sketch that picture, you should see that the energy of the products is higher, right? And let's see, in an exothermic reaction, the energy of the reactants is lower, right? So this one should be, no, it's higher, I mean. That one's a little tricky. Or, you know, here I already said that that's an endothermic reaction. So there's just a million ways to phrase these questions. And so, kind of understand that. I mean, look back on your homework, meaning if they're not true, false, or weird questions like this where they're, you know, circle the higher or lower, or, you know, various things like that, then it's really going to be a question based off your homework. So be okay with converting using a mole to kilojoule ratio, or that if you see the amount of energy given in a reaction, that you can use a mole ratio with that, right? Trying to think what else is there. There's lots of little miscellaneous things that I can ask. You know, I could just throw on there just to keep you honest. What are the 8 common gases? Now, arguably, if I just simply put a decomposition or combination reaction on there, that's kind of asking the same thing because they're used in those, right? I don't know. I really have this feeling that the test is simply going to be, 15 reactions. Now, that might vary. It might be plus or minus. 15 reactions and 10 Chapter 9 questions. It might be less than that. The problem is the fewer questions I put, the bigger the points are. So you make one stupid mistake, you lose a lot of points. If I put too many questions on, then the test is too long and grueling. So, I don't know. Arguably, I should be able to put one example of everything on and be just fine. But then there would be only 5 reactions, each worth 10 points apiece. Better not F up. Better not misbalance one single reaction. Whereas I'd rather have 15 reactions at, say, 3 points apiece, so that if you misbalance one, you only lose like 2 points instead of 10 points. I tend to be more a fan of breaking it apart and breaking it up than not breaking it up. Honestly, I really think the best practice that you can do is click on the questions on the online stuff. Have your, if you don't want to bias yourself as to what type of question it is, simply have a friend write the question down on a piece of paper for you or read it to you. For the reactions, those extra 3 practice sheets, those are literally, at least the third one, I just went through a couple years worth of tests and took all the questions off it. So, those are literally test questions. Heck, your homework is test questions. Some year I threaten always, if my class doesn't do enough homework, that I feel like I should just staple all the homework together and give that as a test and be like, if you did your homework, this will be easy. If you didn't, well, I guess it's just as hard as if I made up random questions, right? So look at your types of homework questions and say, could I answer any of those? Do them out of order. Realize that, sometimes if you're on the worksheet that is all double displacement reactions, it's pretty easy to say, oh, duh, that's what I do, because you know that it's beforehand it's going to be a double displacement. When it's all mixed together, like those 3 extra practices, that's where it's real. That's the hard part. So practice helps. Having the big picture helps. Memorizing all the little parts helps, because if you don't know your diatomics, any question with a diatomic in it, you're automatically going to get a couple points off, right? So just kind of keep it all in your mind. I don't know, how many people actually did stuff over the weekend in Chapter 8? It's good. Keep it fresh in your mind. That's the other thing I notice. A lot of times, I feel like if I took the test score in half and said, what percent do people get on Chapter 8 versus Chapter 9, the one that's fresher in their mind is usually the one they just did. So that's why I always say, don't stop studying Chapter 8 just because we're in Chapter 9. Always be practicing a few reactions so you never get rusty. It's not like riding a bike. You do forget. Riding a bike is one of those things, I don't know. I guess arguably you could forget how to ride a bike, but I don't know. I feel like getting a bike out and seeing how many people would get on it and fall. There's plenty of things you can forget how to do, right? Let's see. I'm trying to think if there's anything else. I figure if it's on the homework, it's certainly fair game. And I got to be honest, if it's in the chapter, it's a fair game, unless I specifically told you it's not on the test. But I think we kind of covered everything on the chapters pretty well. I don't know, is there anything else you want to do? Technically, class is over, but I'll leave it running if people want. I'll put a question on the board. Maybe we'll stop taping it just because we're just really doing random stuff. Well, we said that if you really want to have the best feedback on it, you should finish it